popular request. Hello, hackers. Yeah, you like it, guys? Okay. So, this is office hours. We are on our second week of microarchitecture exploitation. The assignment is due in, what, 4 days? 3 days, something like that, Monday evening. So you do get this office hours, and then there are office hours on Monday, which I feel bad for Adam, but that is your last minute Hail Mary to see if you can get this solved. So I had one thing in particular that I wanted to talk about, and then I asked the people in the room here what they wanted to talk about, and they didn't want to talk about anything. They're just like, I'm stuck. And so I'm not quite sure where I want to go with things right now. If anyone on the stream has a specific question topically, throw it out there, and I will try and incorporate it. But first, I'm going to talk a little bit about 14, which is what none of the people in the room showed up for. And what I'm going to talk about isn't necessarily even like about microarchitecture exploitation, okay? One of the things that is true on these challenges here is we have challenge descriptions, right? And so if I click on 14 here, before you mash start and practice, maybe read what we say the challenge is. It's a hint as far as approach. Okay, someone does say they're working on 14 now. But they're not deep enough to have a question yet. Okay, that's good. So 13 and 14 are both meltdown challenges. One of the things related to meltdown that I had some people ask was if I...
Rob, your stream is focused on right now.
OBS is bringing me down? OBS is. See, I don't know what causes that, but I do know how to fix it. It's because I opened with Hello Hackers instead of, is this working? Let's verify. Yeah, we're getting there, I gotta transform, fit to screen, and then bring it down here. Computers, man. Okay, so you see me there, and Twitch now shows me as well. Okay, and hopefully this hops. It does. Okay, so 13 and 14 are meltdown challenges, and there were a couple things that have come up as people have kind of talked to me about these challenges. So 13 says, use meltdown to read the flag from the kernel module's memory. Now, interacting with the kernel is apparently something people are having some problems with, but if we did the kernel module from 466, we should have some familiarity with ioctl. I can definitely run through how that works if we need to. But the interesting point here is that the flag is in the kernel's memory. Meltdown, what makes meltdown meltdown is not necessarily what I demoed in the literal sense, which confused some people. So in my meltdown here, my meltdown proof of concept, we were doing, where was the guaranteed seg fault? Right here. We didn't have a branch like we have in Spectre v1, right? Where there's this conditional branch that may or may not get executed. Spectre v2 is speculating on an indirect jump, right? Meltdown doesn't require that we do this out of order execution. What makes meltdown meltdown is the fact that userland can leak kernel memory, okay? And the reason that that occurs has to do with how the translation of virtual memory to physical memory works and how that check for am I the kernel or am I userland works, okay? And this demo here doesn't go into the kernel, right? The secret page here is right here in userland. And so this isn't verbatim, right, a meltdown exploit, because we're not leaking kernel memory. But I wanted to show something that is straightforward as far as how can we write our own C program that does this speculative execution all on its own. In order to be meltdown, I wouldn't be trying to leak secret page. I would be trying to leak some memory address that is in the kernel. And so the difference here is that you'd need to be leaking an address in the kernel, and you want to have the kernel be accessing that memory address. If the kernel isn't accessing that memory address, we get into some deep-seated what happens with memory in the MMU, in the TLB, and all of these components that you are free to learn about, but I really don't want to have a lengthy discussion on it. So it still follows a similar logic of access a value and then measure the timing. Uh-oh. All right, that works. There we go. I was just too quick for it. And so this is 13. And if we take a quick look at, this is apparently not 13. Oh, wait. They're still named funny, aren't they? Yeah. Okay. I thought that was fixed, as I had discussed that. But that probably looks like it hasn't made it to prod yet. Okay. So if we open the kernel module here, and we take just a quick look at ioctl, well, I think the device, or the init, actually has a nice little printout. Let me make this a string. I don't care that much. Okay. So we will connect to the VM, and then if I look at dmessage, we can just see it there. It's easier. It tells you this challenge allows you to misuse the kernel in a certain way, and it says it supports interactions through an ioctl interface. This one doesn't tell you what the interface does, which is unfortunate because that is what I was hoping it would do. Instead, what we see is we have the ability to make the kernel access a byte of the flag inside this kernel module. Right? I'm not going to trace through the pseudocode, but that is what we have the ability to do. Somehow, by calling ioctl, we can make the kernel grab a byte of the flag and then use it to access some memory. Right? And so we can use that in our meltdown exploit to leak. And so the pattern, our loop just becomes trigger the kernel to access the byte, then perform the measurement. And we just do that for each byte. In my opinion, it's a bit more straightforward than the Spectre exploits, because with the Spectre exploits, you have to trigger certain behavior in the target. It's speculating over here. We have to train a branch predictor. Yes, question.
Would timing be faster compared to userland?
The question is, would timing be faster compared to userland?
Userland access.
Userland access.
So accessing userland memory versus kernel. That makes sense.
No, I know what you're going for. And the answer is doing the ioctl into the kernel is pretty much real time. And you don't need to yield to it, right? Because I'm the one that's calling, it's my userland process that's calling device ioctl. And so we no longer have kind of this race. The race existed because they were both in 1 through 5 because they were both userland processes. And you only had one semaphore to trigger behavior. Like I could have given you more semaphores and we could have turned it into this like complicated handshake of like increment this one, then sem post here, then sem wait, then sem post. I didn't want to do that, right? Like that becomes this weird exercise in using semaphores. But for Meltdown, for your Meltdown exploit, if your code calls ioctl on the kernel's file that's exposed, that's going to go from your userland process into the kernel. It's going to execute that code inside of the kernel, and then it will return from the kernel back to your userland process. So now I don't have a race because that is all in line,
Yeah.
right? And so your loop is just a tight while loop that is just while device ioctl, measure, device ioctl, measure, right? And you can just do that in a tight loop. And so we don't have to worry about the timing, which is one of the reasons why the original challenges, which is what we see here for like 7 through 14, used the kernel, right? And so the kind of argument there from a challenge design perspective is it easier to just say, start off with kernel stuff and you don't have to deal with these race conditions, or can I give you something friendly in userland that simplifies a lot of the stuff for you, right? Simplifies a lot of the steps, but you can race yourself. So in some ways, I think the 13 is easier. 13 is definitely easier than 12. Probably easier than 11. Like I would suggest taking a look at 13 if you are like reach this point in the Spectre challenges where you're like, I don't know, man. Like just walk away from it, go look at the Meltdown challenges, because it is going to use, which there's only 2, they use the same primitives, but it's a bit more straightforward as far as what you're doing. Now, I said that in 13 here, your loop is just device ioctl to get the memory access inside the kernel, and then it is perform your measurement, right? Perform your speculative access and get your timing measurement. 14 does a little bit more here. If we read the challenge description, it says leak the flag via Meltdown from another process after getting the address of its task struct from the kernel module and using it to find and walk its page tables. So there's a lot more going on here, right? I said that Meltdown is about being in userland and leaking stuff that's inside the kernel, and that's true. But what this challenge is kind of asking you to do is leverage Meltdown to leak a value that's in another userland process. But Meltdown doesn't do that directly. Meltdown only lets you access kernel values, right? Addresses from the kernel's perspective. And so this challenge requires you to have some idea of, well, what is the task struct, right? How does this thing come into play? And so that's what I want to rant about a little bit. Question from Twitch here. Am I holding class live? This is live. This is not class, it's office hours, but functionally they serve the same purpose. So if we take a look here at the kernel module for level 14, and I just want to get this out here. I know you guys want to talk about like 7 or 9 or something, but I want to get this out here for anyone that has made it to 14. The device ioctl in this case, and the challenge works a little bit differently. So 14 does provide you a little bit of information about how the ioctl works. It says here this module has 2 ioctl commands. 1337 will touch a memory address. So you have the ability to specify a memory address in the kernel space, and it will access that memory address. The second thing that you can do is get the address of a process's task struct by PID. And so I could give it a PID via this ioctl interface, and it will give me the address inside the kernel of the task struct. The task struct, does anyone in the room or on Twitch happen to know what the task struct is? Oh, we got a winner. What is it?
This is a structure that contains every information about the process, like the real user ID, effective user ID, and all that stuff.
Okay, so I'm going to paraphrase a little bit here, but the answer was that it's a struct that contains a whole bunch of information about the process, such as the user ID, the real user ID, the effective user ID. So it has some data, and one of those things are permissions. Okay. Now, if that's my knowledge, and that's a totally reasonable definition of it, right? I would say something very similar. That doesn't necessarily help me reason about this prompt, right? Does anyone have an idea of where I would go or how I would figure out how to reason about this task struct? I assume you don't know, right? I don't know. Okay, I'm going to look at the source. I like it. Does anyone know what site we would go to look at the source? So this is something that we're going to see throughout the course. A lot of the slides that I release have links down at the bottom to this site here, elixirbootling.com, which is a great online resource to browse kernel source code, libc source code, any of these type of things. Right? I don't expect you to know all of libc, right? I don't know all of libc, but we can use this to look at the things that we are interested in. And so what I was interested in was task struct. You'll note that I'm over here on Linux. This happens to be right now on version 6.72. Right? We could find the whatever version we wanted if there were a difference in versions that we were interested in, which for like heap stuff, this certainly is the case. What we see here is it'll tell us where it's defined and then where it is used. I'm going to look at sketch.h, and what this gives me is the C source code for this task struct. Now, if you've never looked at kernel source or like libc source, this is going to look insane. And that's because it is. All right, nobody in their right mind can really read this without spending a little bit of time looking at it, because we're going to have a lot of these pre-compiler directives like if def and if, and it shows, okay, well, is this here, is this not here? But we can look at it and reason about what is in this task struct. And so, okay, maybe or maybe not, there's thread info. There's some state. Something about wakey, okay? The task struct is the kernel's internal representation of like some, it doesn't even have to be a process, but like a process or thread, some work that needs to be ran. When we talk about the scheduler and schedule yield, it's the kernel that's doing that. It's the kernel scheduler. And so what the kernel scheduler is doing internally is juggling all of these task structs and being like, okay, you get some work, and then, okay, you're done. I'm going to hang on to this. Okay, this other task struct gets to have some work, right? Now, we don't have to necessarily know all of the specifics there, but that's kind of what its purpose is within the kernel. Somebody says ptrace, there's a ptrace value that is interesting. This is probably, and I don't know this, but my guess would be this is just an indicator of if the process is being ptraced. For those that don't know, ptrace is how levels 1 through 5 do the magic that they do. It's also how GDB manages to kind of manipulate a target when you're debugging it. The underlying kind of mechanism there is via this ptrace syscall, which is insanely powerful, but also insanely convoluted. Okay, if we keep going down here, what I care about is memory, right? Because the prompt here was, we're going to use it to walk page tables. And so I'm looking for something related to memory. And if we did some Googling, we see this task struct has a lot of stuff in it, doesn't it? Hopefully, we see the canary, which is interesting, right? The canary that you would get on the stack, right? Your stat canary, that is saved in the task struct. That's how the kernel knows what it is. And so there's lots of interesting things in here, but for our purposes, what I'm interested in, if I can find it, did I go too far?
Is it the MM struct?
It is. That is what I'm looking for. Did I get past it?
You scrolled
I scrolled past it. There is a struct that is named MMM here. Okay. You know what I'm going to do? 800? 877? Okay, good. So this MM struct is what I'm interested in. This pointer, and we know it's a pointer because it's star MM. This is a pointer to a region of memory that has this MM struct. And I can click on this and say, well, I want to know, well, what is this MM struct? And this will show us what the MM struct is. Now, the thing that we care about within this MM struct is PGD, which I don't remember what it stands for, page something or another. Now, one of the things that we talked about, not we talked about in the class, but like on the Discord was brought up in, I think, further learning. See if I can find it. I should have bookmarked this because I don't know. Firefox is not my normal browser. Gosh dang it. Let me look.
Resolve itself.
Did I misspell it?
Yeah.
What do I need?
Instead of an O, you need an A.
So, like that.
Yeah.
There we go. Okay. This page, which I'll add to the module page, I'll add a link to this after office hours here, does a great explanation, and this is by Zolotul, who's on the Discord, and he is a PhD student in the lab here at ASU. He did this great write-up on how does paging work, right? What is a virtual memory address? How does virtual memory translate to physical memory? And if we could scroll down here a bit, he tells us that we get some virtual address. Well, we know that the underlying kind of unit of memory is a page, right? And we know that the first 3 nibbles index into that page. So what do these other bytes mean within that virtual memory address? Well, they can be broken down, and this is a great write-up, and I'd recommend everyone read it because it's good stuff. Like if you were to just ask me the stuff that's in here, I wouldn't be able to tell you. Like I would reference this, and then I'd tell you what my translation of this is. Because this isn't something that I do every day, but it is something that this individual does a reasonable amount. And so the remaining bits of a virtual memory address is split up into 9-bit sections. And each of these sections refer to an index into some like master translation page. And this shows how we can take a virtual memory address and get these values, these offsets into this translation. Hey, this says PGD. That's very similar to what we had right here. So from the task struct, we can get to this MM struct, which we can then get to this PGD pointer, and that begins the process of translating that virtual memory address to a physical address. And once we have a physical address, we can access that value from the kernel. Because the virtual address doesn't really exist in the kernel, right? The virtual address of the process, because every process has its own virtual memory space. And so, I don't know, hex 1337 in one process may reference one physical page in one process, and hex 1337 may reference a different physical page in another process, right? But the physical page, the physical memory, is consistent. And so what we can do, because we said Meltdown allows you to leak values in the kernel, is once this module, or this kernel module via ioctl gives us the address of the task struct, we can use Meltdown to leak the pointer to the struct. And once we have that, we can use Meltdown to leak the pointer inside the struct to the PGD. And then once we have leaked the pointer to the PGD, we can use the process that is shown here to navigate the PGD to get to the next layer. And all this is you get a value that is an offset from the PGD, which will give you the address. This is an example here of the PGD. So if this is the beginning of the PGD, it's a series of values, and one of these values, part of this value, is the address of the next tier of translation. And the reason that this is good is because he shows you, like, hey, here is what that value looks like. So if we go up here and look at this, notice these all end in 6, 7. That's because the least significant bits are kind of these setting values, right? Where what you're probably interested in is the address of the next, I'm going to say page translation page. And so you can go from the PGD to the PUD, from the PUD to the PMD, from the PMD to the page table, and you eventually get to a physical address that is what is actually backing that virtual memory. And so that is your strategy for level 14. But the underlying principle of what you're doing is still just ioctl measure, right? So if you could write 13 and leak a value where we tell you where it is, right? Like you know where it is in the kernel, we're just doing that and then applying a bit more complex logic as far as how we're using it. Now, one of the things that you might ask, and it would be a totally reasonable ask, is that's great, Robert, you showed me these structs, but we just said that the source here is insane. How do I translate this source to some offset into a pointer? Like if I get, let's go back here, let's just look at the first translation here. So this is in the task struct, and then somewhere in here was Oh, I shouldn't have done that. Oh, you told me it was 877?
Yeah.
Boom. How do I know how far from the pointer to the task struct is this pointer? So there's a few ways we could do this, right? We could look at all the source and say, okay, well, an int traditionally is 4 bytes, and then the union of this thing is, I'll have to figure out what this thing is, and it's going to be so many bytes. And like, we could do this, by hand and try and guess our way through. That sounds like pain, and more than likely we'll be wrong because like the size of an int isn't standardized, and we don't know what pre-compiler settings, which of these are we actually going into, and which ones we aren't. And so that sounds like a giant endeavor of pain. So what can we do? Well, as the very nice blog post here describes, they even call out pwn.college, that if you use pwn.college or you have the kernel running in a VM, which we do here, you can use, as Twitch highlighted, GDB. And so we can fire up GDB on the kernel. And if you go all the way back to GDB debugging, right? One of the great, this was the first module I got to like influence and narrate. Brings me back to the good old days. One of the things you can do is if I have an arbitrary pointer, right? Like I have RSP here. I can cast this as a specific type. Does anyone remember how to do that? It's a goofy syntax, right? Because like the things that you typically use is like, okay, I'm going to print the value in the register, and then I'm going to like examine whatever is at that address, right? This is typically what we think about. But GDB lets us do some cooler stuff if we have symbols. And in this case, the kernel does have symbols. Now, RSP, for the record, is not what I'm going to cast this to. But GDB doesn't know that, so it's going to let me do this. I can cast a value. I know this is a task struct. So we use like a C-style syntax to cast this. But I don't want to cast RSP to a task struct. I really want RSP to be a task struct pointer. And so that's what I'm casting here. And if I do that, well, that didn't work. And that's because you have to say that it's a struct named task struct. Right? We have to use proper C here. It isn't, what's the word that I need? Where you can redefine a struct as so you don't have to put struct. Type def. Yeah, it isn't type def. So we have to say struct task struct pointer. Okay, well that's great. That was super helpful, Robert. Now it just says struct task struct star. Right? Well, what can we do to pointers? We can dereference them. So if we complete this, dark art incantation here, and we cast RSP to a task struct pointer, and then dereference it, GDB doesn't know that this is a lie, right? Clearly, RSP is not a task struct. I want to be very clear about that. But if you work in the challenge, it will give you an address that is the task struct. And so you could perform this same operation. And my gosh, did that just yeet a whole bunch of garbage to the screen. Okay? Well, so let's scroll up here. And because GDB has the symbol information for a task struct, it knows for this version of the kernel that is compiled and running on this system, what are all the members of this task struct? And not only that, it knows what are the like makeup of the structs that are pointed to, and like it's giving me something that looks sane here from a structural standpoint. I mean, everything is C for whatever reason, but that's what I get for like casting RSP to this struct that it clearly isn't, right? Because casting a pointer just says we're going to pretend as if this struct begins at this address. Now, somewhere in here is MM. The MM pointer. Right here. Right here's my MM pointer inside that casted struct, right? So how do I know what is the distance from where the struct begins to this pointer? I can print it.
One trick is to use RSP, use address 0, and then access MM and then get an address.
R0?
Yeah, instead of using RSP as address, you cast 0 as task struct, and then access MM, and then use the ampersand symbol to get the address. That will get you the offset.
Okay, like you're going in the same direction that I'm planning. I just don't know about this 0, where 0 comes into play here. So like if I do this, it says I can't access memory address at 0. That's why I used RSP, just so I know it's a valid.
Dereference it,
Don't dereference it.
and then you put the whole thing in a bracket and then access MM.
So I do this,
Yeah.
MM.
Yeah, so it says offset is
Okay, I'd like that. That isn't what I was going to do, but it was going to be the same logic, right? That's actually cleaner than what I was going to do. That's awesome. That's a good trick. And so yes, that does work, because what is indexing or accessing a member of a struct? It's taking the base address plus some number. And so what this trick was is we said, okay, well, let's pretend the struct begins at 0 and just add the offset into the struct. And so that worked pretty well, right? Now I know the distance from the task struct to get that pointer. And so if I were to then contextualize that with our lie that RSP is where the task struct is, which it is not, we could say that the pointer is at RSP plus hex 3E0, right? And this probably won't, it'll probably just say C's, which as we scrolled up is what the task struct or the pointer was if I were to scroll all the way back up and find it. And we could do that same, I want to try that same trick. What would I need to change once I have the pointer to this task struct? Where did it go? Oh, 837? 877. Okay, so let's say I have this struct. How do I find the offset to the PGD pointer? What would I need to do? Cast the thing to an struct.
And then do the same trick to find the offset.
Okay. So we cast it to an struct pointer. And then what I'm looking for is, helps if I type correctly. It's hex 50. And so now we know the distance to go from that pointer to the PGD. And once we have gotten to the PGD, we can follow this nice blog to explore how this kind of translation works. But it's still just going to be a series of leaking some value, doing some math, leaking another value, doing some math, and hopefully if you do get to this challenge, it kind of opens your eyes to like how virtual memory and physical memory relate to each other. So I wanted to talk about this. Twitch says there's kernel protection against null deref that protects against it. Yes, in general you can't like dereference null. It's a bad thing, but that's why this trick was clever, because we didn't actually dereference null.
We can also use the ampersand symbol.
Yeah, you can use the ampersand symbol to get a reference of something.
Yeah.
And so there's different permutations of that. The clever thing in that was being able to use the 0 so that you just got the number, where what I was going to do was still base everything off of RSP and then do the subtraction itself. But since you get around that by setting the base to be 0, we don't have to actually do any subtraction, which is why that's more clever than what I was going to do. Okay, let me take a quick look here at Twitch. Thank you for linking that page for anyone that's watching it via stream. Okay, and so hopefully that gives you an idea of how to tackle 14. All right, so that was a brief rant that was of no value to anyone in this room, but hopefully mildly entertaining. Okay, so the next thing, I guess, would be 7 or 7.1. 7 is honestly kind of a joke. It's bugged, so like you don't have to do what it says. That's why there is a 7.1. Last year, when bugged challenges got solved, I wouldn't patch them, which is how we ended up getting like these weird, oh, this one is bugged and then this one isn't, right? Yeah, that's why I changed the policy this year. Functionally, they're the same thing. So if you solve 7.1, it'll also work on 7. Now, the 7 is interesting because it is not a Spectre exploit, and it is not a Meltdown exploit. I don't think it's even speculative as I think about it. It is just a timing attack on the microarchitecture. Okay? And it would be really lame if I were to do this, but if we go, actually we don't have to go there. It's embedded on the site. If we go down here to flush and reload, make sure I'm muted. Hopefully this doesn't spam anyone. We see my smiling face here. Somewhere around this mark, see if I can find it. Right here. From this prefetching slide onward, I talk about how we can use the prefetch instruction to determine whether or not memory is mapped. And not only do I talk about it, there is a nice little demo here, which I could, like do live here, but then I'm going to make typos and it's going to be just gloriously a mess. So I'm not going to do that in order to save myself the embarrassment. But what we see here, the important part, is this kind of how this measure function is structured. See if I can zoom on that. Boop. There we go. What we see here is it is a very similar setup, all right? We are capturing a timestamp. We have a fence. This could have been an M fence, right? And it wouldn't have broken anything. This M fence could have been up in front of this timestamp, right? It doesn't have to be verbatim what I'm showing here. But in spirit, this is one example that does work for this. And so we're getting a timestamp. We have some fences to prevent speculating, and we're performing this prefetch, getting another timestamp, calculating the time. So what are we doing here? Well, we're timing how long it takes, not for a memory access, but for this prefetch instruction to occur. And if I move a little bit forward in this video, boom. What I'm doing is I am running this on a region of memory that is before and after, right at the edge of an address that I'm mapping. Let's see if this prints out the mmap address. Okay, it doesn't. But what we see here, okay, it does, right? No. Right at the beginning, it says mmap return something or another, which I briefly scroll up. Oh, yeah, right there. We see mmap returned 5820000. And so I called mmap, and this returned some virtual memory address. And so this virtual memory address that we see up here exists inside the process. Then I am doing this measure the time of prefetch, and I am looping through memory addresses.
Hey YouTube, this is Robert from the future here. I misspoke a bit during this live session, and so I want to make sure that I'm spreading accurate information. If we look at the timing values here, and again, we're kind of measuring the time of this prefetch instruction. We start at virtual memory addresses that are mapped within the process. And we observe timing values that are somewhere in the range of about 600 to 700 here. But as soon as we kind of jump across this edge of virtual memory addresses that exist within the process to virtual memory addresses that are not mapped within the process, and this occurs right around hex 85,000 to hex 86,000 we see here, the timing values change from that 600 to 700 range to suddenly being 1,000 plus. Now, this is, definitely what I got in this particular run. You'll want to try and figure out where that threshold is or what the difference is for yourself. But we can use this kind of measuring prefetch timing to figure out what addresses are mapped within a process versus which ones are not. Now, this is a brief explanation, and if you do want to, kind of dig into this or get more detail, I'd highly recommend that you watch the video that I am kind of discussing here, the original one, which is the microarchitecture flush and reload.
Am I on? I'm on broken pipe. I think I started 7. Let's see here. And so if we look at 7, I think I'm on 7.1, but like I said, they are the same thing. Okay, so it doesn't blatantly tell you what's going on here. So we do have to use some of those mad debugging skills to figure out what's going on in this bad boy. But what we should see I always get worried when that Dojo dev channel suddenly like has mad commits flying by. It happened last week as well, and I actually requested that we don't make any major changes between the hours of 4:30 and 5:30 p.m. on a Friday, so that this exact scenario wouldn't happen. But alas, here we are. This makes me very sad.
Did it actually break?
Yeah, it's not loading. So I don't know if it's because there's like a 365 deadline or mad 365 push, or if it is due to some breaking change. But like I know at a high level why you would see this error, and it is like in general a 500 error is like the server screwed up, right? 400 is you screwed up. 500 is the server screwed up. And so if you see a 500 error, it's on us. Give me one moment while I at least ping some people and express my frustration in private. Okay, but if we were, no, I don't think we got owned. I think we just had some YOLO commits, and I certainly have done a few.
It's the self-owned.
What's that?
The self-owned.
The self-owned, yeah. So what we would see if we had the ability to open this in Ghidra. Makes me sad, is that this program maps a random address, right? And then our goal is to find where in memory does this mmap occur, right? And if we were to reverse it, we would see that there is some range. I imagine I don't know, right? So I'm speculating here. We would see some called the RAND, and so there's going to be some address range where an mmap is going to occur. Based upon that mmap, we'll either be able to know what the flag is, or we're putting flag bytes at some mmapped location. And so we can use this trick here of timing prefetch to figure out where in virtual memory this occurred. And again, the logic there is not, that's an amazing snippet of me. The logic there is not particularly crazy. If we were to look at that measure function, it's a very similar logic where we're getting a timestamp, performing some action here, and then getting another timestamp. It's just we're measuring a different assembly instruction. Okay. I want to believe. While I am waiting to see if this reappears, does anyone have a general question or something specific that I might be able to answer from the top of my head? I talked a little bit about 7 for the people that were on 7. Does that make some sense as far as like what you're trying to do? Yes? Okay, cool. If over the weekend, you're like, hey, I'm trying this, it's not working, post on the Discord. Right?
It's a pretty active 7th thread.
Okay. Like, I write my little blurb, and then I just assume, if I don't hear anything else, that like things are going reasonably well for people. If you don't say, everything's on fire, this doesn't make sense, like, I don't know to help you, right?
I think we're back up.
What's that?
I think we're back up.
You think we're back up? Okay. Let me see if this. Okay, cool. So we had to kill all the challenges. So I'll fire 7 back up again here, and we can take a look at it in Ghidra or Ida. Started. All right, things work. Yeah, I kind of want to just use Ghidra going forward, but I won't do that today. Like, I'm thinking about making a personal commitment to Ghidra, all right? Because there are some very cool things that Ghidra can do that people just don't know about because nobody uses Ghidra, right? Like none of the senseis. And I'm not saying I know all of the super cool things, but I know people who do know the super cool things. And so I can find out and then replicate what they do so then you can see it. There was a question, how do I distinguish previously allocated pages from the desired one? So you wouldn't. The only thing that this kind of prefetch strategy earns you or gains you is it a valid memory address, right? Now, one thing that you could do is reason about the virtual addresses that are present. Let's see if that is a sane strategy. So hopefully we know that if we fire something up in GDB, we can take a look at VM map, right? And this shows us the virtual memory addresses that are currently mapped in this process. Now this is at start I. So we haven't mapped that region. This is practice mode, so I should be able to run this in sudo. And if I start I, we look at VM map, I continue, we VM map again. You'll notice that there's a pretty big difference here at start I versus over here. Now, part of that is because start I is before like anything happens in the process. So now we have these libraries. We see libsepcomp, we see libc, we see all of these libraries. So maybe that's not the right place to do. Thank you for the compliment on the shirt. I never know if people get the references or not. This isn't the right place to do that comparison because there's a lot of changes in the mapped virtual memory between start I and right here. So maybe I run this. Well, let's break it. What, mmap? No, let's go back to Ghidra. Let's see if we can find a reasonable spot to do this. So, welcome to the challenge. This is going to mmap. Some buff. It's going to map a page. Okay, and so it maps this flag page. Now what's interesting here with mmap is this is mapping file descriptor 3. And file descriptor 3 is what? Probably the flag. Just from context here, looking at this error message. Assert flag FD equals 3. Okay. So, okay, right here. We are mapping something to this 13337 region. And we're mapping a page. Okay. And so that is for the shellcode. What was going up here with the flag? Well, it maps it to if you're unaware, which the answer is to look at the man pages, the first value of mmap is like a suggested address, right? You're asking the mmap call to return a pointer at a specific location. So give me a page of memory, and the program is saying I want it at whatever this buff pointer is. Somebody says, why GDB when you can statically reason about it? Don't make me turn this into a GDB class. Okay, just don't do it. And so we want to know, where does this buff value come from? Well, buff looks like it is from dev-view random. And so it is going to get it's going to read 3 bytes from dev-view random into buff. It's going to bit shift it by 16 bits, and it's just going to say, all right, that is where we're putting it. And so this gives you some idea of the region that you need to check. And we see here that the return pointer is v7, which v7, if everything went well within mmap, should be equal to buff, right? So it's going to have this random address where this is mmapped. But what's happening with the flag? Well, we are calling open on the flag. We're asserting that that returns file descriptor 3, which is great. We're going to read 3 into v7. So we're going to read the flag into whatever location this mmap occurred in. And so this can inform us about where the flag is. If we were to scan these low addresses, right, there's definitely an upper bound here on what we can get from dev-view random. At least I certainly imagine there is. And we'll find the flag there. So this is inside the challenge. If we were to VM map, there should be something that is a single page of memory. I imagine we mapped it read-write. This looks like a good candidate. I don't know that it's correct. It might be somewhere else, but let's just give it a shot. Okay, it's not there. Is the flag chilling over here? No. Is it up here? I would expect it to be a single page of memory, but I'm not seeing that.
Where's the breakpoint?
All right, so the mmap occurs before the shellcode reads. All right. So right now the challenge should be blocked on. Oh, you want to break at the mmap? That would be smart. How dare you? So in practice, I find just use grep.pwn.college. Yeah, you could also use find. Like, there's things you could do. So I find breaking on mmap sucks because, generally speaking, when you're mapping pages of memory, a lot of this happens during initialization. But we can figure out where this is, which it says, what, 171D. And then did this de-randomize? No. So I would have to get this base address because I didn't copy this, which means the addresses are still randomized. It should be this address plus the offset into the binary, which is hex 171D. I'm a giant liar. Why am I a liar? This doesn't have symbols, I'm sure. Wait, does it? No, we don't have symbols. Okay. Whatever. I'll go the long way. Go to main, find the call. What did I say it was? 171D. Right, but this doesn't tell me. This is why I just live in GDB. That's a setcomp. Here's the mmap call. There's that. Well, no, this is the mmap call for the shellcode because we see the read and close up here. And so this is reading into that address, which means this needs to be a valid address before the flag gets read into it. So there should be an mmap call above this. So this is the mmap call that I'm interested in. Oh no. Where was it? Printf puts read, mmap, main plus 334. Is that where I am? Yeah. 334. Continue. We'll go to the next instruction and we print RAX. Okay, so there it is. Ah, it was hiding up here. I should have just thought about I should have been like, oh yeah, we read 3 bytes and then we shift. Yeah, it's going to be a small number, so it's going to be at the top here. And what do you know? This is 1 page. You guys can call me out if I'm doing something just utterly ridiculous, you know. So now we have that address. And so if we continue until we get blocked on the shellcode, now it should be read in, and we can examine the string at that address, and we see that the flag is read in full at that location. And so what the challenge is requiring you to do is write shellcode that will use that prefetch instruction to figure out what address is getting mapped. Once you find that address, your shellcode can just print out, or what do we get, exit?
Yeah.
If I remember right, I think we set comp exit. So you'd have to use exit as a side channel to communicate 1 byte at a time. And that means that since you're calling exit, you'd have to do this several times for each byte that you want, right? Loop through the prefetch, figure out where it is, find the offset into the flag, leak the byte via the exit code. All right. All right, I'm not sure there's a side conversation there. So yes, that is 7 in a nutshell. Hopefully, strategically, that gets you where you want, where you need to be. The hard part now is implementing it, right? Just writing the shellcode. It's going to be a couple for loops. Shouldn't be too ridiculous if you've written shellcode sometime in the recent. Okay, what else was asked? I started late, I'll run late. I wanted to rant about 14. There were some people that were on 7. 8. You were an 8?
I just finished 9 while you were talking. I'm doing great today.
Oh,
It's
see,
good
it's what osmosis, proximity,
Exactly,
right?
yeah.
The wisdom just emits. Yeah. Okay, so you're just cruising. 8. All right, what do we got going on here? So 8 is where things start getting kind of interesting, right? Because we're not doing the tutorial. The kind of logic here, which I think I mentioned on the slide deck in class, 8 is Spectre v1, 9 is Spectre v2, 10 is Spectre v1, 11 is Spectre, no, I'm a liar. Why am I a liar? Oh, no, okay. 9 and 10, this is why I had a slide, are just flush and reload. Okay. But the logic is that there's a Spectre v1 that is just in the x86, and then there's a Spectre v1 that is in Yon code, and then there is a Spectre v2 in the x86. That's more straightforward. Then there is a Spectre v2 in the Yon code. So let's see what 8 actually is, which used to be 3. I think I'm going to rename them to something that just doesn't have a level. But they'll at least start with like Baby Arch. I still like that convention. Okay, so what do we have going on here? Let's take a look. Somebody on Twitch here says a couple things. As far as 7, there's a comment that they think the exit code is 32-bit signed, 32-bit signed integer, so you can expose up to 4 bytes at a time. So someone's optimizing. Another comment, 8 is very similar to 5, except you have to set it up a bit. So, what do we get here with 8? Well, I've got a kernel module. So, I know I need to connect. I need to type correctly and then connect. So we're in the VM. We'll take a quick look here. dmessage. Dmessage tells me generic nonsense, something about ioctl and mmap. So this is going to probably work similar to what we've seen with kernel modules, or in particular, toddler sys, which might be why it was a requirement coming in the gate here. So we see that if we call mmap, it's going to return some private data, right? It's going to give us some pointer into the kernel. When we ioctl, we get return 0. Now, for this challenge, this tends to be where people just, oh no, I hit tab and IDA just, right? And this is why having a deeper understanding is helpful, right? What for anyone that hasn't solved this, what do you think you do at this point? Read disassembly or use Ghidra. Or not disassembly, yeah. Hit tab? Yeah, okay, there's my pseudocode. And then, tab will take me to assembly. I've never used tab in that direction. Tab only makes it go, it's a, oh no, it's a one-way operation, man. Okay, let's try this newfangled technology. Oh, okay, big things, big things. So, we see here that there is something going on inside device ioctl, right? And if we've seen how 5 works, then we might be able to make some sense about what's going on here. Does anyone have any idea what these things are?
Probably slow instructions.
Okay, they're probably slow instructions. Can we go any bit further there? Like I would have to look them up to tell you exactly what they do. But what can we kind of just at a high level? What do we think? What kind of operation is going on here? I guess.
Division.
Okay, that's a good hint. All right, we see div ss. All right, div probably means division. Do we know anything about these weird XMM registers? Like,
Do they hold floats?
floats. So floating point numbers don't get, when you're like computing on them, they aren't in your general purpose registers. There's this whole other like subset of registers that you can use for floating point and like SIMD operations, which aren't things that you commonly see in reversing, because it's not typically in challenges, right? But it totally could be. And that's where these XMM registers come into play. And so what's going on here, and I don't know what CVT-SI2SS, I imagine this is moving the value from a general purpose register to a floating point, a register that can do floating point math, right? And that's what's happening here. We then are performing some division. I have no idea what is going on there. And so we're doing some type of floating point math, and then there is a conditional jump. Why in these challenges have we seen weird floating nonsense, right? Well, you hit it early. It's just slow instructions, right? We have to batch out to this floating point subunit of the CPU, and maybe it gets us an answer, or maybe it doesn't. So what'll happen here is, more than likely, the CPU will guess. And so we have a branch here where the branch predictor will come into play. So we have to reason about what is happening here. We may have to like Google what is div-SS, right? Is it XMM1 divided by XMM0 or the other way around, right? I'll leave that to you to figure out. And then how can we influence these? Well, we'll take this one. XMM0 comes from RCX. RCX is whatever was at RDX. RDX is whatever is at RDI plus this offset. RDI is whatever it was when ioctl was called. And what do we know about RDI as far as functions being called? What are calling conventions? Argument order. Okay. So this is accessing some value that is an offset from not necessarily the file descriptor. If we look at this right here, it's file star. So it is a pointer to the kernel's file, right? And this is at offset hex C8. And so it's grabbing some value at some offset there. What's the other value? RAX. Oh, you're doing something crazy there. CS prefix length. It's madness. Right? And so maybe there's two ways we could approach this, right? There's the proper way where we can sit here and read what every single one of these instructions do and do a ton of Googling, and that's totally great. You know what else we could do? Right, we could run it and GDB it and just see what's going on here. Be like, okay, what happens if I give ioctl this? Right? What happens if I put something into mapped memory? Because remember, we do have the ability here to call mmap, and it's going to return some pointer into the kernel, right? And so we could hang out here in static land and you know, figure it all out, and we'd probably in the long run become masters of the universe because we would know every single assembly instruction. But personally, I would just throw GDB on it and try some values, step through it, print it out, and try and just reason about it at a high level. Let's not get stuck in the details there. But hopefully, we can influence this somehow. And if we can influence this somehow, then we now have the same scenario that we had in level 5, where we have a branch that we can get it to think is going to go one way and then make it go another way, right? So this is a Spectre V1. And if we look here in the happy case, because it's green, what will happen is this will grab some byte out of the flag, and then it's going to perform a memory access based upon that byte. So RDX here is some base pointer, right? We'd have to look right here. RDX, RDI plus C8. Well, what is a base pointer that we might think about? Like, what is a location that might be interesting to offset this file? Well, I don't know that this is the case, right? I don't like to look at the solutions when I ramble about this stuff. It's way more fun to do it this way. Well, we have some base address and then it's offsetting into it, and we know that RDI here is the file pointer. So it's accessing some member of the file pointer. Well, what does mmap do? Well, it's going to return, this is the file pointer, which is RDI, which goes into R8, which is then, it's moved right here into RSI before that VM malloc is called. So it's probably accessing some offset of this shared memory that we can mmap. Remember, for these speculative access, or these, these cache side channel attacks, what we're measuring is memory access time. And so what memory do we want to measure access against? Probably whatever this mmap is returning, right? In the userland kind of tutorial challenges, the challenges are just like, hey, here you go. Here's here's some magic shared memory that it's gonna work. In these kernel challenges, it doesn't inject it for you, but we can call mmap on this file, this kernel device, and it's going to give us some region of shared memory. And when we look at what is going on inside the device ioctl, we see that a flag byte is being used as an index to access shared memory. And so this is that same pattern that is a Spectre gadget, which should be mentioned in the lecture material, like the pre-recorded stuff, as well as the official Spectre paper, if you took a look at that. Right? It's this pattern of having some secret byte and using it to index into memory that allows you to perform that side channel attack. As far as 8, does that clear up some of the stuck points?
I have everything implemented, but I don't know why.
I did everything right, but it doesn't work. That is the classic problem in this class. That problem exists in 365, 4.6. It doesn't matter what we teach. People do everything right, but it just doesn't work. So when it comes to those type of scenarios, I tried to replicate that a bit in class, right? With my, here's some stuff that doesn't work, what could we try or reason about? So my question to you is, what do you mean it doesn't work?
So if I'm not speculating, if I don't call the speculative function, and if I just access the syrup index, I am linking the character F correctly.
F?
Yeah, so before the flag, there's a prefix, which is like flag in capital. So I am linking the first character, which is capital F. But as soon as I access the first index of the actual flag, which should be B, I'm just getting values that are all over the place.
Okay, so I'm going to repeat a bit for Twitch here for the recording. The statement was, I'm doing this. I'm able to speculatively access, and when I access index 0, I'm getting the byte that I would expect. Apparently, which I didn't pay attention to, but apparently this, probably on device init, it tricks us. Oh yeah, okay, a init module. When it reads in the flags somewhere in here, it is going to prefix it with some string.
There, it's in the move instructions.
It's hiding in the move instructions? Oh, wait. Tab goes this way too? Madness. Okay, so yeah, it has this prefix here, flag. And then that is existing here. And then the flag value is present. And so what they're saying is I can get this F, all right? But I can't get P, right? I assume you can get L, A, G, okay? Which is cool. Have you figured out what's going on with those crazy instructions I kind of hand waved?
Yes.
I don't want to spoil too much, so let me just ask this. And I don't know the answer, but I'm going to hypothesize here because I know how we write things. If I get F, am I speculating?
No, I'm just accessing.
I'm just, okay. So
I can try that.
my prompt here was, if I am accessing this F value, do I need to speculate? Okay. And the reason that I ask that is because what I want to know, and I don't know that this is the case, but I would be willing to bet if we poked at it in GDB, we have to hit tab and go back to the assembly. There is this comparison, right? My guess, and I have no reason to guess this other than just guessing, right, is that what makes this work or not work is if the index is like above 4, right, or below 4. And so if the index that you're accessing is zero, then it's just going to access it. It's just going to, yeah, all right, cool, we'll load up F. This is great. Right? But if I can't access the P of the flag, the issue is in the training, right? Because we aren't getting that speculative access. Now, one of the things that I saw the other day while I was helping someone with 5 was you have to remember that the speculative access isn't going to occur every time. In fact, a lot of the times it's not going to occur. And so we have to make sure that our logic is aware of that, right? You could run it 1,000 times and say, well, whatever I see the most, that's got to be it, right? What happens if you failed 999 of those times, right? The most common case is going to be the wrong case. Yes?
How do we define failure in this case if we're just looking from an outside perspective? Because like we can't see what the CPU is doing, right?
Right.
So like how do we know we failed speculatively?
Well, you would know it from the timing data. The timing data is the only thing we have to infer about what is occurring inside the CPU, right? And so I'm not saying that like 200 is a great number or 300 is a bad number, right? But this is all about kind of relative grouping. Now, if you took a strategy of, I'm just going to take the lowest. Well, if we failed speculatively accessing something, everything's going to be, I don't know, say 300 to 1,000, right? And so you'll get the quickest thing that wasn't in the cache. Well, that's not very useful, right? There should be a, I don't want to say substantial, but definitely observable and measurable difference between a cache hit and a cache miss. And so you could hard code a threshold if you wanted. You could say, I'm only accepting it if it's below 150 or below 200 or some number, right? And that's not a bad way to go, because then you're at least requiring something to be substantially lower than what I commonly see. Now, what that number is, could you hard code it? Absolutely. A more complicated solution may try and speculate, look at all the data, and be like, what's the lowest thing I saw? What's the average thing I saw from the high numbers? What was the lowest thing I saw? And dynamically calculate a threshold for this CPU at this time. Because remember, those values are going to change based upon how busy is the CPU, right? I typically, just by the nature of my sleep cycles, I'm typically up at like 2, 3 a.m. And so that means when I'm doing this stuff, the timing data that I get is going to be very different than you running it at 10 o'clock as 365 is writing an infinite loop in assembly for the first time, right? And like we've all been there, we've all done that, but it's going to impact you. And so it's your job to account for that. Whether that means I'm going to print out this information right now and then change my hard-coded threshold based upon observations that I've seen right now, or I write some fancy thing that's going to dynamically figure that out. Now, you run into this kind of problem with, well, what if I just set the threshold to be like 2, right? Some like insanely low number. well, I'm never going to get a hit, right? And if I set the threshold too high, I'm going to get too many hits. What you can do is set a, this is Goldilocks and the Three Bears, right? You're going to set that kind of middle threshold where, okay, like most of the time, if it's less than this, it's a hit, and then I can sum that in reason, right? But just taking the raw lowest or saying I'm going to do a fixed number of iterations, and then whatever I got out of these 1,000 runs is it, will be error prone. Because you have no guarantee that 1,000 runs is enough to get data that makes sense. I didn't show it on stream, but last week during office hours, I kind of brought this up with level 5, which I don't write. I know there are some people on the Discord that are writing like super hyper optimized solutions. The intended solves here that we have is like proof that the challenge isn't broken are not super hyper optimized things, right? They're just, okay, this like roughly works at a conceptual level. It's not super fast because I don't expect you to write some super hyper optimized thing. It's great if you can. And like if you do, I'd be curious to see it, right? Because I think that stuff's cool, but that's not the requirement here. The requirement here is to just get the job done. Somebody posted a meme about like their solution solving it in 20 minutes. And like, I don't care, you solved it, right? I think the cutoff for the dojo is 6 hours unless you repeatedly log in, right? If you can solve it in 6 hours, right on, run it and go to bed. People did that for the 466 side channel attacks. Right? People are like, I leaked half the flag last night. This is great. Right? If you did that, that's great. It works. Flag is flag. Right? But to give you, I think I blew it away. Okay, because that 5 isn't this 5. Oh, okay. We're going to gamble here. And hopefully it is this file. Okay. This is the like check for this. Well, we see here that it's not super fast, right? I'm not doing 1,000 runs and getting the value, right? My high level strategy here is I'm going to loop through each position. If I haven't determined that it is something, we're going to give it a shot, right? We're going to try and speculate it. And if we get it, we find something that hits our threshold, cool, we're putting that character here. If we didn't get it, it's all right. We'll just try the next one, and we're just going to loop through everything that I don't know infinitely until I have confidently decided on every byte of the flag, right? And so your high level logic there can definitely influence how messed up your output is. Now I could run, if I ran this like 30 times, I'm sure it would result in an errant byte, right? It would leak something that's wrong. Most of the time it's correct, but this is at a threshold where it totally can make a mistake. The other thing that you could be doing wrong is just not training it correctly. Right? Like that's the more direct answer, is I know I'm getting the value when it's accessed, so I know I'm getting this timing right, but I'm not getting it when I need to train the branch predictor. And the training for these should be, I don't have it here anymore, but in that ioctl, I assume we got to set that index value somehow, right? So we set that index value to be F. We hit that 10 times, right? Now then we switch it up and go for, I think it'd be like index 6 or something. That should be that P. That is one attempt, that whole process, just like 5. And so you could be training it wrong if you don't understand how that mechanism is working. You should be able to reasonably hit that though from GDB, just making sure that you're hitting the other path, right? You're setting the index correctly and getting it. Because
training, I'm
Okay, okay. So you, okay. So I'm gonna repeat for Twitch. The comment was I was training things correctly, right? I know I got that right because it's the same logic I used in 5, which is good. That's why 5 is what it is. So you can hopefully understand how that training process works. However, my kind of measuring logic as far as what I was doing with these observations was suboptimal. And so now I'm kind of reworking that to hopefully interpret the measurements or only count measurements that are clearly indicating something. And so hopefully that leads to a flag. All right, I have up to 15 more minutes that I will talk. Anyone got anything for me?
I have a random unrelated question.
Random unrelated question. Let's see what we get.
So you know how like page faulting occurs when you do translate from virtual to physical?
Okay.
But if you just work with like a physical address, you don't have to worry about page faulting.
So the question was, page faulting occurs when you translate from the virtual to physical memory, and I'm going to kind of put an asterisk there and say when you're like writing to it.
Yeah.
Okay, specifically, because I am pretty sure that if you are just reading some page that has no requirements, the kernel will just lie to you, because it can. I have broken this camera. And so the question was, well, what if I just use physical addresses? Right? Then I don't have to worry about page faulting. So my challenge to you is get a physical address from userland.
Yeah, that is the challenge.
Right? Like if you can do that, you're 100% right. Right? But you can't. Right? And within userland, physical addresses don't exist. Right? Physical addresses don't really exist even like in the kernel. Like they do, but they don't. What you're accessing inside the kernel is an offset from a virtual address inside the kernel that maps to one-to-one the physical address, right? There is a location in the kernel that is phys-base, right? So just like how I give you in the tutorial challenges, here's shared memory and it starts at 1337000, right? Inside the kernel, there is some virtual address that is just, this is 0 for physical memory. And so when you say I want to get the physical address, right? I want to access physical address 0. What you're really accessing is phys-base. And if you say I want to access physical address hex 1000, what you're accessing is phys-base plus hex 1000, right? It's not that physical memory is directly addressable inside the kernel. It's that all of physical memory is mapped in a contiguous fashion inside the kernel's virtual memory. Does that answer your question to some degree?
Yes.
Okay, good question. Like these are the cool things that like I like when people ask, because it means like you're thinking about this. And hopefully it's something I don't know, because then I get to go like bug other people and try and figure it out myself. Then I get to learn it, which is why this is a fun class to teach.
Like
Because
the IDA tab.
yes, exactly. I learned 2 good things today from you guys. I learned about IDA tab, right? I can go back and forth. It works 2 ways. And I learned in GDB, I could just cast the struct to be at 0 to just get the offset, which makes total sense, right? Like after we did it, I'm like, yeah, this is obviously the way to do this, right? But it wasn't what I do, right? And that's great. Like that is hopefully, as everyone continues just playing around in computer science, you pick up these cool tricks, right? That's what makes it fun. Twitch chat says phys-base is hex, oh, I can't read, FF 888 and then zeros. So it is apparently a fixed location here in the kernel that is known. But remember, if you're in user land, you can't access any memory addresses where the highest bit is set. So any of that FFFFF, right? That's all kernel memory, which you can't directly access unless you're using Meltdown. I remember for the Meltdown ones, you need to be in the VM. Okay, anyone else? Twitch, it's been a few moments. Hopefully we aren't time dilating too hard here. And if you had any questions, you'd hit me with them. Anyone else here in class? Going once, going twice. I am going to release the format string module later this evening. I don't think I wanted to add some harder challenges because printf is pretty straightforward, like as far as how to deal with those type of exploits. And what used to be the hard challenges, which were super cool, right? Like the hardest ones, some entrepreneuring hackers here on the dojo submitted a PR to pwn.college that makes it way easier than it used to be. Right? So you used to have to like implement all of this complicated logic on your own end to like calculate and think about the implications of the later challenges, the requirement that it has. But now pwn.college just will do that for you, which is cool, right? Like it's cool that it's out there, and it's cool that it was a result of our challenges. But now I'm like, well, where's this hard thing that I'm gonna people are just gonna get stuck on. And so I had some ideas, but I haven't had time to do it. We'll see what happens there. But I will at least release the module in its current state later this evening. And again, that will be due, 10 days from now, roughly?
1 week by 1?
Yes. Yeah. So the intention here is everything through the rest of through spring break is 1 week, if I remember right. We'll see what happens once we get into heap, as far as how people pick up there. That's a bit more pointery stuff. I don't think it's too hard. There is a module, the primitives and memory mastery, is a bit of a grind. So we'll see how much you guys complain about that one, because that one it's not meant to be a toddler module, but it kind of is, in the sense of, okay, you have to not only do heap stuff, but you have to do race condition stuff, you have to reason about this. There's a lot of pain in that module, right? And so it should be pretty smooth sailing until there, which would be just a week of pain, and then we hit heap 2, which is less pain and way cooler. Like, once you get done with heap 2, it'll be cool, right? Because heap 2 is when you fully understand kind of how the heap works, and you get very accustomed to at that midpoint in the semester with dealing with arbitrary write, arbitrary read, creating those primitives, and manipulating pointer values, right? And we're going to do that already with format strings, and then we're going to do that again with file struct. But you really kind of see it by the time we get to heap 2. But yeah, everything is slated to be 1 week. Heap 2, maybe we push it into spring break, if you guys want, because it's slated right now to be done, I don't know, a day or two into spring break. And it makes no difference to me if we push that out for you. I want you to enjoy spring break, but if you want to work on heap stuff, right, for credit, I have nothing against it. And then, as Twitch says, after heap 2, there is Windows. So that is what's slated on the schedule. I intend on that being what happens on the other side of spring break. I may make some changes to the second half. I have been talking to some people about things that we could do that could be fun and interesting. We'll just kind of stay tuned for that, right? But there will be some Windows in the second half for sure. All right, with that, I believe I have pretty much used my time. I appreciate everyone hanging out here with me. Again, if you do have problems, please cry on the Discord. It's the only way I know how to help you. Otherwise, I just assume you're just procrastinating. So, That'll leave you. Goodbye and good luck.